Another draft physics video presentation. So I guess we'll just use this ElectroBOOM video as fodder for presenting the counter argument and just presenting the idea that they really have no theory for the function of these basic elements of our reality. Gravity, bent space is just kind of a non-descriptive. Doesn't make any sense in 3 dimensions, as stated. Doesn't account for the energy, blah blah blah. Magnetism, same thing. You got this phenomenon, you know things move, and they have to be compelled to move by something, and so they just call it this ambiguous force, but they don't give it any kind of definition at all. They just say there's some sort of magnetic force and some sort of electric force, and this force somehow produces attraction repulsion without any definition of how it does that. And as I've pointed out, they have the idea right. In this electric and magnetic, they can create 2 different forces. And that in some way accounts for the fact that there's 2 different reactions, repulsion and attraction. Those are the 2 choices. Come closer, go further away. Less pressure, more pressure. So again, it's about a field, a gradient pressure field, and those are things that they should be talking in context of, because it's just kind of obvious this is about pressure. Pressure moves things. That's kind of a fundamental rule of physics, and they just have no interest in exploring theory regarding what's causing the pressure, what the pressure might be made out of. And they, joke about their cluelessness as if it's okay to be clueless, which is, but the whole idea of the joke, I mean, it does work. I mean, this guy's 3.3 million subscribers, so do a little buffooning, and that impresses the masses. And apparently the physicists too. People just can't get on with life in any kind of serious way. Just get to the point. Now you got to throw some candy in there. You got to put sugar in every meal and salt and all that kind of crap. And I hate to resort to that, but maybe I'll start to make some once a week videos that are for the people that need to be entertained. Really pathetic planet. Anyway, I could dress up as a coronavirus. It'd be funny. Yeah. It's so stupid. Anyway, so without further whatever, so we'll just, who knows what subjects we'll get to.
Do you want to do magic? You can try this at home. No, really. I have a 1.5 volt battery. I have a white LED here that requires around 3 volts to turn on, so my battery can't turn it on. Now I put 3 of these LEDs in series, which means they need 9 volt to turn on. The battery can't do shit now. I have a regular
Yeah, couldn't do shit with 1, right? Can't do shit with 3. Shit, yeah, we all need to have that explained to us. So he's taking an adapter and taking it apart.
Transformer wall adapter not connected anywhere. You can use it as is, or you can tear it apart and pull 1 coil of winding out. Either way is fine. Now the positive of the battery goes to the coil that goes to the positive of the LEDs and returns to the battery.
Right, so he threw some of the metal, kept some of the metal. Okay, so because it really won't work with the extra, without the extra metal. So he's not going to say anything about that.
Or you still can't do shit. But now, if I short across the LEDs with a piece of wire and let go, bam! I have 9 volt pulses.
Right, and the pulses happen when he's disconnecting the voltage. So when it's shorted, there's not enough voltage to do anything, so it doesn't mean anything. And the whole point is that when he lets it go, the coil has stored energy. Well, that's what the metal stuff is doing inside the core of it, right? So again, they didn't do it with just a plain coil. Didn't explain any of that a plain coil isn't going to store any magnetism, because it's going to be in a form, okay, in a field where it doesn't store energy well at all, very little. So, so he left that part out, that yes, the metal has been magnetized by the core, and when you turn the voltage off, it takes time for the magnetic, for all the little dipoles inside of the ferrous material to release the energy of moving. Their movement will be the energy you're getting back out. The coil will pick that up and produce a voltage based on how much energy it's releasing, how quickly. But it'll be more than 1.5 volts.
Across them, and they turn on. And here I can replace the coil with the wall adapter, and doing the same thing, it's even brighter.
Yes, because there's two coils. Yes, and the metal's all in one piece instead of broken into pieces. I didn't think it was this stupid, but okay. I mean, some of the stuff he does is kind of advanced. It's kind of like, a bizarre mixture. Doing this, whatever this part is, this little patronizing part. Are you really, really stupid, or really, really, really stupid?
Magic. I wonder if it can shock me. Here, instead of the LEDs, I put my fingers across the wires and short across my fingers. Well, yeah, I mean, I can feel it, so there are pulses of high voltage. There's a new way to get shocked. I've shown you before that medium magnets drop like a rock in air. But if you drop them through a roll of aluminum foil, they drop very slowly.
Right, so something else I don't think he's going to touch on is this huge difference between what ferromagnets do and what the paramagnetism is, in the sense that one is the opposite of the others. The atoms that are already magnetized, like iron, that are already polarized atoms, they just move in the field, right? They align with the magnetic. I hate to say the magnetic field, because you're going to have that silly notion that magnets are doing some sort of field thing, so I don't want that confusion. So north end, south end of the magnet, and the little magnets will line up because there's a repulsive force that's attractive to the opposite. So all the little magnets will line up exactly the opposite, okay, to the field, or their position to the field. And opposite would be here. So they will, everything in the field is going to be the opposite magnetism for regular ferrous material. But if the material is not already got a bunch of polarized atoms, then all you're really doing is saying to something else, I'm hitting you with a bunch of this X energy, and I'm hitting you with a bunch of Y, zero energy, or whatever you want to call it, this opposite energy, right, from the other side. And the thing is going to exactly fight back, in the sense that you're putting a kind of pressure in. So, whether it's low pressure or high pressure, you want to think about it as pressure. You're pressurizing the other source. That is, you're pushing the atoms, the electrons, because this is electron repulsive here. So you're pushing the electrons in on this side, and you're pushing them out over here, but you're pushing the protons in. And so all you're really doing is switching how much pressure the electrons are under. And obviously when you do that, you have the mechanism where, in this example, there's a dipole, but obviously you could turn the magnet this way, obviously, and have one end of the magnet, as is traditionally done, one end of the magnet facing the paramagnetic material. So you're either pressurizing or depressurizing the electrons on the surface, and by pressurizing them and depressurizing them, you can force a voltage. Now, obviously, when you pressurize them and don't move, then they just stay pressurized and they don't do anything. Nothing changes. But as you change that pressure, then the pressure moves through all the other atoms, and that's where you create a current. So if you keep moving the magnet, you'll keep changing the pressure on the electrons, and by changing the pressure on the electrons, that pressure will move between all of the electrons. All the electrons are essentially connected to each other. Every electron knows where all the other electrons are. They all feel it because there's a force being provided by all of them towards each other, and it's a force proportional to their distance. It gets weaker with distance and stronger the closer they get. And obviously this electron, if this one was closer, then it's going to move this way to find balance between these two directions, and the same here. So every electron is always connected to every other electron, essentially, that's available. So if you have a vacuum here, well, then it can't connect to that atmosphere. But if you have an atmosphere, then it'll also leak that pressure into the atmosphere by a rate of how dense the atoms are. So the denser the atmosphere, the more conductive it is, the more likely it is to move the pressure into anywhere it can go. So, but in a confined wire, you'll tend to just move it through the wire. So that's it. That's the correct explanation. And they're going to think, oh no, it does some kind of this thing, and it's field lines, and it's no, just a force, a radial force emanated. It's charge. It's just charge. There's only one thing. There's an electron and a proton. They have charge, and when you align them in a dipole, you have magnetism. When you keep them as charges, you have charge phenomena, electricity. All right, continuing. So again, he should have said something about the fact that this magnetic phenomenon is very different than the magnetic phenomenon of iron, for example, in the sense that it's an opposite. The thing you hit it with, you'll get the same thing back. So it's a repulsive field created by paramagnetism, where it's a complementary field, that is, the magnet turns opposite to maximize attraction, when it's a iron field, an iron or a ferrous material.
But similarly, look, this frame is also made of aluminum, and my magnet has north and south on the surfaces, and if I put it on and let go...
Right, so all the little magnet is doing is it's creating magnetism in the aluminum forward of it as the field moves, as it radiates. It's a light bulb. Think of the little magnet as a light bulb. It's shooting red light onto the surface of the aluminum. The aluminum's saying, can't deal with that, and it's a repulsive field that generates back, and the magnet's sticky because of adhesion. So the adhesion force is stronger than the magnetic repulsion. So the magnet's sticking to the aluminum because it's a flat surface, and the magnet's a flat surface, and the field is in front of it. So there's a repulsive field. It's pushing pressure into the aluminum forward as it moves, and as it moves, it's pressurizing those electrons, but it can only pressurize them so much, so it's just reflecting the force back and forth, and it's repulsive. So yeah, it's probably worth drawing that more specifically. So it's not sticking to the aluminum. It's clearly the north side of that little magnet. They're usually polarized north-south on the flat sides. So what's happening is it's sticking to the aluminum because it likes sticking to flat surfaces. All right. So, but what it's doing is it's pushing a force in that's reflective to the bottom of the magnet. The bottom of the magnet is pushing back with the same force. And so the force reflects, gets trapped between the front edge of the magnet. This is happening right on the surface of the magnet. So it's not extending down far. It's right on the surface of the magnet. So it's this little surface right here that's feeling all of the drag to its progress, because at this real little point there's a bunch, it's like the ping pong paddle argument. You've taken two things that were pretty far apart, and there's a ping pong ball trapped between them, and now you're making them very close, and now they're having a lot of reflections. So you've turned something that was allowing some of this energy to get out, it was going through the paddle, and now you've made the paddles very opaque to each other, okay? And so everything caught between them is now reflecting back and forth, and it creates a lot of resistance to movement and such. Yeah, appear to be back. Cold outside. Anyway, continuing.
See, it goes down slowly. Magic! You can make a few turns of winding and connect an LED to its end and drop it on a wireless charger, and bam!
Yeah, some more, not terribly interesting kind of crap. And this whole wireless charger crap, maybe they ought to just talk about how kind of inefficient they really are, in the sense they're shooting electricity, the field change over this whole surface, a whole bunch of energy going absolutely nowhere, and only a small percentage is captured by the coil, blah, 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 blah.
Magic! You stick a battery on a magnet and short the battery using a piece of wire like this, and it starts turning.
Yeah, we did all that stuff before. So yes, we all are learning all these little toy gimmicky things. Very exciting.
Magic. You connect two parallel reverse LEDs across a coil and pass a magnet through it, and ping pong, ping pong, ping pong, ping pong. Magic! Of course I joke, it's not magic, it's magic. Oh, it's
Yes. Yeah.
magnetism. Stay with me to the end to understand.
Right. So again, stay with you. Well, no, you're not going to explain anything. So why not? Why not just concede? You have no clue how it works, and all you do is know some of the footprints it leaves behind. They know some things about it. Like you could argue like invisible tyrannosauruses could exist, and we could deduce some things about them because houses would suddenly crush and these giant footprints would be left behind, and but they really have no clue what the invisible thing is.
Understand what's going on. Stay. Magnetism is quite simple at noob level, which we strive for here. When you have charges moving in a direction, you have current, and magnetic fields wrap themselves around that path like this.
So that path is kind of a clever way of saying that the electrons have a path within a medium, a conductor, and that the same thing might not be true for electrons on their own. That they aren't, they always have a field. They're charged, and you can move the charge to different locations. And when you move the charge, it has a consequence to all the other electrons the electron is connected to. So the idea is you can't move one electron in the universe without moving all the other connected electrons, the ones that are close enough to have a meaningful relationship, like the moon and the Earth. If you if you had two Earths orbiting each other, three are connected to each other, but if one's 500 million miles away or something, you can't have much effect. But anyway, it has some effect.
Going to infinity. This follows one of the right-hand rules, where the thumb shows the direction of current, which is the flow of positive charge.
Right, so this is where they screwed up electricity. So instead of just pointing out, well, because we mislabeled electricity, in terms of the positive and negative end, the end that has more electrons, the end that has fewer electrons, because we messed that up and assigned the wrong labels, now we're going to pretend current goes in the opposite direction of voltage. Doesn't make any sense.
Charges or reverse of electron flow, and other fingers show the direction of field.
There's a reverse of electron flow, so so why don't you just take account for where the electrons are flowing? Why don't you fix that? Because maybe by fixing that you'd figure out that these two fields aren't what you think they are. They're charge fields. There's the magnetic monopoles and the electric monopoles are the same monopoles. They're called electrons and protons.
Wrapping around the wire. So if the current runs in a loop like this, magnetic fields wrap themselves all around the wire like...
Alright, so now we're back to this wrapping field kind of crap. And there is no wrapping field. What there's going to be is the radiation, the light, okay, is in two forms, this red and blue. And they cancel each other when they become purple. That is, they cancel each other for an electron or a proton, depending on what it's getting hit by. It has the opposite effect. But I mean, this idea that there's a current running through a wire and then there's this field created around the wire going around the wire, it's just wrong. The wire itself is just radiating, okay, red or blue, depending on the orientation of the wire. And you can have the consequence of purple. But the idea is that sometimes the purple is made out of this just keeps switching from red to blue, red to blue. So when you take a wire, the other thing you can another thing that again you can see in the real world and that it fits, just like the tipping point argument fits the behavior of electrons, why they're frequency dependent, can be understood as a simple tipping argument, that each thing has a certain tension and the tension it's in will decide what frequency you hit it at to constructively add energy on resonance. Its resonant frequency is essentially the frequency at which you're most capable of adding energy to it. So if you have a wire and you curve the wire, so we'll take a wire and we'll curve it. Obviously you have a higher surface area on one side and a less surface area on the other side. And what's really going to happen is that the electrons are going to go to the part of the wire I don't want to say that explicitly. What's going to happen is the dipoles are going to align based on the fact that there is a difference. And depending on what there is to reflect off of, what you put inside this coil or what you do, you'll change that. But the point is that you can sort of obviously just understand that there's going to be the two sides of the wire aren't going to be the same. They're not equal anymore. And so the charge of the, if there's not an equal balance, then obviously there has to be an imbalance between the protons and the electrons in terms of how much space they occupy. So the more irregular you make a shape, the more likely it is you are to create an imbalance between the density of the protons and the density of the electrons, because that's the safest way to say it. And when you do that, you're changing the pressure between the electrons.
Like this. And that's why some metals like iron have stronger magnetic properties and are called ferromagnetic.
So it's not really. The reason why is because they're polarized atoms. The atoms are dipoles, and decidedly, in the sense that they're definitely blue on one end and definitely red on the other end. And the more definite that is, the more a magnet they are, and the more they will turn in a magnetic field and complement the field, because they'll turn to make attraction.
Because this cloud of electron turns around the atom core in a more defined direction, and
so this is all stuff they just made up. So he calls this noob level magnetism, when this whole theory that electrons even move around atoms isn't proven, let alone this theory that this, whatever this stuff is, these lines represent what the magnet is actually, what the thing is actually producing. So in a sense, this drawing is sort of an illustration of the fact that you can understand an atom could have two dipoles. It could be polar in two directions. So if you had the protons here in the middle and you did split the electrons over here and over here, you have more positive here and more positive here. So you have red radiation here. So you have decidedly more red on these two ends and decidedly more blue on these two ends. So essentially you have two magnets, two polar fields, any way you look at it. Okay, so you have blue, red, blue, red, blue, red. So you can make a blue-red combination here, or here, or here, or here. And then you got the other dimension. So the magnetism is more complex, the field. It's like taking bar magnets and crossing them. And then you could add a third bar magnet. And so now you have more than one. You have a north-south, north-south. It's more complex than just being a stick magnet.
Turns the atom into a tiny magnet. But see, when the molten iron cools down, it solidifies and crystallizes into this patchy crystal form, with every tiny patch having a random magnetic direction.
Right, but see, it wouldn't have a magnetic random direction if you put a magnetic field across it while it's still hot and let it cool. Then they'll all freeze in the right position. And some soft iron, so this is the difference between hard and soft, or even stainless steel and steel, is the harder you make it, the harder you make it to magnetize. So the softer, meaning the more liberty the domains have to move, the more magnetizable it is. But it's not like some underlying principle, because the harder I make the steel in the first place, the less likely it is to be magnetizable. once it's frozen, once it's solidified.
So all these random directions cancel each other and the iron is neutral. If you bring a strong magnetic field close, you force these to rotate and align with the field, which not only
So align in the opposite way. So understand all of the field lines they draw are really opposite magnets because they align in one direction. So when he's doing that, he's basically showing that all of those red to blues are all aligned in the same direction and creating a polarity that's exactly the opposite of the polarity of the original magnet, not the same. So he's doing it kind of cheating by just pointing the north end, because it gives the illusion that they're aligning with the first magnet, and they're not really aligning with it. They're doing they're not going to strengthen that magnet. They're going to do the opposite. See, so I mean, if you draw it this way, where both fields are active, instead of having a north end pointing to those magnets, the domains are really doing this. They're lining up exactly the opposite to the original magnet. Well, I already drew this, right? So I shouldn't have to draw it again. Okay, so they're not going to be complementary. This magnet isn't going to make this magnet any stronger. If it lined up the opposite way, it would, but it's not going to this way. So these are the field lines. So let's understand the field lines are exactly the opposite, and they're opposite each other. So as I pointed out before, the reason why there's a gap between where the iron filings line up is only because these magnets repel each other. So there can't be a solid line because they're opposing each other in the sense that the way they're lining up in the domains. So that's sort of, it gives you the wrong impression. It gives you the impression that the magnets line up with the original magnet, and they only do that on the north end, and on the south end do they make a continuation of the magnet, but on the sides it's not it's a complete opposition magnet. Well, even on the top end, right, they're all turning south. Well, yeah, so they're north south, so they're the magnet this way gets a little stronger, this one, because the other magnets are lining up in the same way, but everything on the sides is obviously exactly the opposite orientation. I mean, it's sort of important to understand the magnetic field created is the opposite polarity of the magnetic field the magnet produced. The new magnets are producing the opposite field.
If the original field, it turns the iron into a magnet. But it's like these tiny magnets are stuck on a spring, and if you bring an external field close, they try to align themselves. And the stronger the field, the further they align, until...
So it's kind of, I mean, they're not aligning themselves beyond the fact that they're doing exactly this. They're aligning with each other because they're all being hit by the same strong magnet, makes them all the same kind of magnet, and the same magnets repel each other. So they have to realign north, they have to align staggered to be able to be complementary to each other. So you have to stick the magnets to each other, north end to north end. Well, I really shouldn't have to explain all that, so I won't bother.
They fully align. This is when the magnetic material is saturated, meaning that stronger external field won't make any difference in their magnetism. And when we try to remove it...
Well, yeah, I don't know how you figured out that you already did that. Saturated just means you only have so much mass, and the mass is producing the light, so to speak. So the more mass you have, the more rays of light you can produce. And there's only so much. You can line up everything so well that all the red is going this way and all the blue is going this way, but there's almost so much blue light you can create. So what you're trying to do is eliminate the purple by pointing the red flashlights all one way and all the blue ones the opposite way. So you have the least amount of purple, and that's your strongest. The strongest you can make that particular magnet is to have all the flashlights, no flashlights pointing in erroneous directions.
The external field, they try to spring back, unless too much force has bent them permanently out of shape. So when you have a piece of ferromagnetic material and you connect a magnet to it, it becomes a magnet too. And if your source field is strong enough, you can bend those tiny springs out of shape and make a more permanent magnet. Of course, heat is the enemy of permanent magnets.
So especially neodymium ones, they won't come back. A regular magnet will. So if you do that to a steel magnet, an iron magnet, you can heat it and then let it cool, and it'll go back to where it was as a magnet, because the domains are, the impression of the domains is already a comfortable place. It works, so they can go back easily. But neodymium, because they're ceramic, and I'm not quite sure. I think the domains are further apart from each other, or whatever the exact reason is. But once you randomize them, they won't just spring back, because the same pressures don't exist to spring back. So a neodymium magnet would be destroyed by heat, where an iron magnet will survive.
Because the structure shakes out of alignment and the magnet dies forever. There. So don't overheat your magnets. Goodbye, love.
So, jokes. It's not a bad joke.
Ouch! Not everything hot is kissable.
Yeah, so that's a good line, Oh, that's bad news. They won't let me not play the ad.
It was Michael Faraday who was first able to imagine and observe magnetic fields as these invisible lines, and then later...
Right, okay, so I've been over this whole thing, that this was really the first, this is where you made the whole thing incomprehensible forever and ever, because Faraday made a mistake, and he did a lot of good things, did a lot of right things, and he did one little mistake, where he kind of confused charge. They understand as a radial force, they understand it, okay, pretty much, that's how they draw it, that's how they understand it, they get it. But then when they put two opposite charges, the proton and the electron, with their opposite fields, the opposite effect of their field. So again, let's go back to the blue and red thing, okay? So one is producing blue, one is producing red, blue and red. They lost sight of what it's really doing, which is just shooting rays of stuff that either reflects off another. So if I put an electron here, you got the understanding would be is that it's a constant reflection back and forth, back and forth, back and forth. The bit of energy gets trapped between an electron and an electron. But an electron and a proton, so if I put a proton here, that force doesn't get trapped, it leaves, perpendicular. And this force goes back and forth, back and forth, back and forth. The red. So this thing reflects red, this thing reflects blue, and that's why you get this strong repulsion, is because you're basically just saying the energy can't get out of here. It just keeps going back and forth because it's a perfect reflection. And so then the point is that yes, these fields will line up. That means you want to avoid these pushing away things, and you want to maximize the attraction. That's the comfort zone of the thing. So obviously, if I align a proton and electron with a proton and electron oppositely, there won't be any repulsive forces. Nothing will be doing the hate you thing except for these long directions. So all the short directions will have no repulsion, and only the long directions will, and so it'll be less pressure. And so they'll just line up. And so those are the field lines they're talking about. This is how dipoles line up in the field. But there's absolutely no evidence anywhere, ever detectable. I mean, Faraday should have known this, that you can't pretend there's a current running through here or something running through here, because it never is detectable. You can't stick something in here and measure that pressure. There's no pressure moving this way. The pressure is between these objects. The pressure is not moving through this arbitrary alignment path. This arbitrary alignment path has nothing to do with anything moving. It just has to do with which way this magnet will be opposite from this magnet. And so they give it an orientation or an arrow, because they're saying, well, if it's electron proton, then we'll put the arrow this way, and if it's proton and electron, we'll put the arrow this way, and we'll pretend something's moving in those directions, but nothing is moving along those lines.
With the help of Maxwell and some other scientists, they put together these complex equations to describe electromagnetism. Forget about this shit. I'm supposed to be educated to be able to use these equations, but just seeing them hurts my brain.
Oh, whatever. Obviously, the equations have some value, but again, they should already know this idea that, you know, like one of the equations says there's no magnetic monopoles, when clearly you want to create a magnet, you just put an electron right on top of a proton. Now with regular charges we can't do that. We can't make a charge dipole, because when we do, the charges exchange their voltage and the thing doesn't stay a dipole. So in space you could probably do it, because you can get two charges really close to each other without them discharging. But that's all the difference is. So of course there are magnetic monopoles. They're called electrons and protons, the same ones that are for charge.
Them at your own risk. But here, I'd like you to really feel magnetism in your heart. Observing magnetism is quite simple, like my examples at the beginning.
Okay, so he's going to now admit the truth. Okay, so good.
Except that magnetism is fake. It's like the shadow of electric fields. And it has something to do with Einstein's theory of relativity. Don't
No, it really doesn't. So you're really being silly now.
worry, I'm not going there. Especially since I don't know what the hell is going on.
Right, so why don't they just admit that? And then say, you know what, that's a big problem. Instead of making these cartoon videos, maybe we want to think about it a little bit and say, where did we go wrong somewhere that we can't make a mechanical model that works for magnetism? You have no mechanism. You have this idea of some virtual photony thing moving in some fieldy thing. You got photons doing all of this kind of crap. You know, the whole thing is mush, and you ought to fix it. And you know, yeah, you ought to fix it.
If you're a professor with clarity on the subject, please help me.
Yeah, well, you're not really interested in help, so, you know, so that's another big joke. You know, you have no clue, you're admitting you have no clue, and you're just saying, yes, who cares?
Put me out of my misery. But for now, forget about everything complex and let's stick to primitive ways. Knowing that the concept of magnetism is correct and makes our calculations...
Okay, just knowing the concept of magnetism is correct. No, your concept is incorrect. You have some evidence of footprints and crushed houses, and so you know there's some correlation between how the thing works. So you know that, well, if you see the footprints, you're likely to see some crushed houses. You know, but that's all you have, is a little bit of understanding about some of the cause and effect links, but you have no mechanism. None. Because you've, you know, bought onto a bunch of woo. You keep making, it's like somebody, it's like the guy who, you know, did the Darwin thing the wrong way, where, you know, the giraffes have a longer neck because they hoped for it. You know, they hoped a lot. They wished they had a longer neck, and that made their kids have longer necks. I mean, you know, this idea of trying to cart before the horse stuff
is very efficient and simplified. So, magnetism is like an annoying partner. It resists any change, like, let me just...
Okay, so this is another one of, this is, so he admits they don't know what they're talking about, and then he starts talking more of their nonsense where they think the magnet is assessing a circumstance and resisting it. No, the ferromagnetic is demonstrating that there's no resistance to change. They love to line up and, you know, do all that stuff. And paramagnetism is what's showing you that, well, if you can't polarize the atom, if the atom can't move to adjust to the field, then it's going to end up doing this reflecting thing, you know, and you're just going to end up pressurizing electrons. So again, electron pressure is what voltage is. That's what a current is. And so wherever you compress electrons or expand electrons, you're going to have something called a voltage. So you have the thing called ground, which is this much pressure. So if I do this to electrons, they're obviously way different than the standard electron, the ground. And if I do this to electrons, put them really close together, they're obviously very different than the ground again. And those are the differences between plus and minus. Just has to do with how close you're smashing electrons to each other. And you can understand that if I have two surfaces covered in electrons, and I have one surface that is really covered, okay, so it's producing a lot of blue but not much red, that the other side is going to end up saying there's a lot of red hitting me, which is going to move the electrons, which is going to pressurize the electron. So it's going to be electron pressure. If it's shooting the opposite color, well, then the electrons feel totally comfortable because they're not reflecting energy back and forth to each other, and it's the protons who are going to have to move.
No, don't leave. Okay then, give me a kiss. What the hell are you doing, you animal? The hell? Let me just go. Don't leave! For f***'s sakes. What the clip is trying...
Oh, yeah, it's humor. So I just don't, I mean, maybe when you're a kid, that stuff kind of works like that. They used to do those little 3-minute little video things in between the cartoons, locomotion thingy or whatever it was called, or infomotion, whatever. They teach you some little principle, and it was all little fun cartoons. But you'd think there would be some point where people would be hungry for something a little deeper. But apparently not. Yeah. Jeez. I guess I don't consider myself much of a grown-up, but I mean, apparently I am, compared to you children.
To say is that in magnetism, according to Lenz's law, anything that's created due to magnetism opposes any changes in its creator.
So again, it's really not opposing changes. It's just that if you create pressure, then you have to release pressure, and you have to create pressure. You can't leave things in one state. If you leave things in one state, nothing moves. So to move stuff, you have to keep changing its state. But there's no resistance to it. You're getting a rational response to it. It's not like saying, oh, it won't change. Obviously, it is changing. That's why the thing creates the change in the wires, because it's not resisting the change. It's completely complementary to the change. So however you change the field around something, it will move to adjust to that change. And the resistance just has to do with how long it takes to move something back and forth from one place to another. That takes some time, so the resistance is only in the time it takes to actually force something to move.
This current through a wire, it induces changing magnetic fields around the wire that create opposing currents in the wire to
Alright, so this is just silly, this opposing currents thing. Wrong answer. All you're doing is polarizing the atoms. So whatever magnetic effect you have on the wire, which is slight, by the way, is only because you're changing the polarity of the atom when you pressurize its electrons. So if you depressurize or pressurize the atom, you're changing its shape fundamentally, right? So I mean, if an atom's sitting here with electrons in certain positions, and I pressurize this electron, which means I pressurize these electrons, in terms of creating less distance between them, which means it's going to leak over to here too, and that's going to get pressurized and push this one over here, and this one's going to get pushed over here, and this one's going to get pushed over here. I'm changing the polarity of the atom. So the atom was sort of balanced between the attractive pressure between the electrons and the repulsive pressure between the electrons, and the attractive pressure to the less pressure between the protons and the electrons. And so you're changing those relationships, which means you're polarizing the atom, which is now you're making it more magnetic. So by moving this electron in, you're making this proton less visible, because now the electron is bigger relative to the size of the proton, so less of the proton is visible to the external world. And so this side ends up being proton side. A little bit of plus, more red goes this way. And the same exact opposites happen here. This electron's moved a little bit away, which has made the electron smaller relative to the proton. So now the proton, or the opposite. Yeah, so now the proton energy is stronger. Sorry, I just did this the wrong way. I labeled this plus when I should have labeled that minus. And so now you have the red force, right? So that when the electron's closer to the proton is weaker. When the electron is further away from the proton is stronger in terms of the amount of dilution, purple. So you're reducing the purple on these two sides because you've moved those electrons. And by, again, moving these electrons, you'll likely move these, so you're also creating a polarization this way and this way. So you're just making it a little more red this way, a little more blue this way, a little more blue this way, a little more red that way. So you're turning the atoms into a magnet by changing the shape of the atom by pressurizing the electrons.
use the changes in the source current. You change the magnetic fields around the wire and they induce a changing current in the wire that creates opposing magnetic fields to stop the changes in the source field.
Right, so none of that happens. You're obviously just changing the atoms by exposing them to a field. By exposing them to just blue light, you affect the electrons. If you expose them to red light, you affect the protons more in terms of the repulsive effect, and you pressurize those. And whatever thing you pressurize can become depressurized, but when you pressurize an atom, you reshape it, you change its shape, and when you change its shape, you create polarity.
Phase current through a wire, they create changing magnetic fields around it that oppose the source current.
Right, so the simple argument is obviously one wire is going to be creating a magnetic field that's going to affect the other wire, and as the other wire gets affected by that magnetic field, it induces a pressure change, and then it also creates more light. So the two wires essentially just communicate with each other and say, so you push a current through, which changes the shape of the atoms, polarizes them. So now there's more blue going here, let's say. And that responds by pressurizing and then causing more blue to go this way, because now more blue is going to reflect. And the inverse happens if you reverse the currents, So you're just allowing this to affect that, and when that affects this, this affects that, so that both of them are going to be tied to each other based on how much they're reflecting versus how much they're allowing the energy to move out of the wire.
Current. Those fields wrap around another wire and induce a changing current that...
So you should always state that this is with, DC voltage, not AC voltage.
Create opposing magnetic fields and reducing them so that they can't effectively oppose the source current. So the source current rises again, creating even stronger magnetic fields so that it can maintain the output current. It's an opposition mess.
Yes, and it's just a word, right? You're not really figuring out why. You're not explaining any details. And then again, the key function is that once you've pressurized a wire, you can't do much with that. Until you release the pressure, there's no way to move it. So once you've pushed something against the wall, that's the wall, it's pushed against the wall, nothing's going to happen. And something can't happen till you release the pressure and allow it to expand again, so you can push it in again and expand again and push in again. That's why you have to use alternating current to induce the effect of current or voltage, because you need to keep moving, causing a change in the pressure. You have to change the pressure to have electric movement. It has to be change for the electron here for there to be change in the electron here. You can't change the electron over here if you didn't first change the one over here, and you can't change it once you've pushed it against the wall. You have to unpush it.
But this feature of magnetic fields is what we use to create inductors and transformers. See,
so now he's just changing the subject, frankly.
Inductance is based on this property that the induced magnetic fields oppose the changing current by inducing an opposing force called electromotive force.
Yeah, so all that's happening is you're changing, the shape is being changed by the electricity going through the wire, but the magnetic field can complement that, or it can fight that. In terms of it can smash the atoms even closer together, or you can do the opposite field, which would expand them again.
So every piece of wire has some inductance associated to it. But to increase this effect, we loop a longer piece of wire like this so that the fields created from each wire wrap around more wires, and this...
Right, so this they think makes some sort of sense, doing that drawing, like that could mean anything to anybody. What do you mean the fields wrap around, blah, blah, blah? Doesn't mean much. So, just doesn't say, well, how does that make anything happen? How does that work? What's happening? And the key to a coil, as pointed out, is that there's an inside and an outside to the coil, right? I mean, that's the real obvious part, is that inside here, so if you were sitting inside the coil and we looked at it this way, so there's a bunch of wire wrapped around. Let's see, that's probably not the best way to see it either. Think. Well, anyway, you know that if you had a coil with a lot of wires, the wires are close together and they're basically closing the surface. So the surface is completely covered with wire. And what do you have on the inside? You have the same effect on the inside, right? So if you look at through the coil this way, you see this wall, okay, that you're going to try to travel through, right? I mean, you know, there's this wall of wire. And so you could understand that if this is all the same, these are all like electrons pointing in, that in here, this energy would just keep bouncing back and forth inside of that closed system now. You've created a wall. So if I leave the coil loose, all right, well then you can say that, yeah, well you get some of that reflection, you know, some of the stuff inside here will reflect, hit this wire, reflect, but then it's going to get out again, and it's going to get out again. So the looser the coil, this is what the math says, by the way, the looser the coil, the less of this effect, and the tighter the coil, the closer together the wires are, the more intense the effect will be. When the effect is this, inside you're just reflecting the energy, so you're storing it. It's like a battery, and the only place it leaks out are the two ends, right? The two ends of the coil. All right, well, yeah, you can see that the light would be able to deflect out. So once the reflections bounced around in here and they got to this edge, they could fly out into space again, so they're free, you know. But that's the only place you're losing it. Otherwise, it's trapped in here. And so the more energy you pump in terms of magnetizing the wire, reshaping the atoms, the more it stays inside. Now, so if you have air inside there, well, air isn't very much to work with, but you put iron inside of there, then you'll make the effect even stronger, because the iron dipoles will all line up with that field and create even more reflections. I don't know what would happen if you put paramagnetic material in, because theoretically it should create, you know, reflections, and in a short amount of distance, you know. So you have the coil, and then you have, you know, the space between the iron core and the wall. You could sort of understand that the more I reduce that space, the more reflections I can end up having, which would also be effective. Yeah, I just haven't. I was just thinking about putting a conductor inside a coil, and but anyway, I shouldn't do thinking in the middle of the video. But anyway, speculating.
Increases the inductance and so the magnetic reluctance against the change of current.
So there's no reluctance, there's a storage, and it takes time to dissipate the storage. So you've changed the orientation of all the little atoms inside the conductor. They're all doing something, they're all pressurized in one way, and when you stop pumping the current, all the atoms are going to reshape to a comfortable shape, and there's going to be all the stored reflections are going to be transmitted through those atoms by keep reshaping them. So as the atom tries to reshape, because you're not pumping wire through the coil anymore, so the electricity is not going through the wire anymore, which means the atoms are now going back to the way they were. But the fact is, there's a whole bunch of energy trapped inside here that's going to keep reshaping them. So they go from, so it creates sort of an alternating current, in the sense that it creates atoms that keep going back to normal. Then the stuff caught inside the coil hits them and reshapes them again, repressurizes them, and then they reform back to round, and then they get reshaped again, and then they get round and reshaped again, until all that energy trapped inside finally goes out through the wire. But it's just like a kind of battery, and that's it. It's a kind of storage device, and you've stored the energy in by internal reflections. By creating a bunch of internal reflections inside the coil, you've stored a magnetic effect. And the same is true with the iron core. The iron core, all of the domains are pointing in this one direction, and as they as they demagnetize, they're going to be doing the same thing to the wire wrapped around. No, not as effectively. So yeah, so it stores less energy when you're better off with a less than hard iron core to store more energy. So if you want to use it as a battery, you need to emphasize the reflections, and if you want to use it as a capacitor or a damper, then you put an iron core in it. I think that would be the difference.
Overall magnetic fields around such an inductor, which is also an electromagnet, looks like this with the...
All right, so there's the lines, right, with the arrows. He knows there's no experiment demonstrating any movement in those directions. So whether it's a permanent magnet or an inductor or however I make magnetism, I'll never be able to make something move on those lines. Nothing will ever move that way. If I put things next to it, if I put an electron in next to a magnet, you know, into the field, it doesn't go in a direction. It goes right for the positive, you know, the electron, the opposite end, the south end. That's what it does. It doesn't do any deflecting in any kind of field. There's no movement around the magnet. There's no energy for that movement. There's no force. There's no anything. So they know experimentally they can't show that that thing exists, and they keep drawing it that way because that's what Faraday did.
Direction of the fields following the right-hand rule, and from north to south on the outside of the electromagnet and south to north inside. So increasing the number of turns increases the magnetic fields and...
No, increasing the magnetic increasing the turns increases the density of the wall. It makes the wall thicker and thicker and thicker. So the more turns in the same space, all right, obviously you can't just say the more turns and then make the turns really far apart. That math won't work. But the more turns in the same space means you're just making the wall thicker and thicker and thicker, and you can trap more stuff inside the walls.
Raises the inductance. Also, a larger radius increases the length of wire, and so the inductance. And...
well, so that's the different kind of proportional math you have to do. So again, this distance would be much smaller though. It wouldn't, if you did over the same amount of distance, that wouldn't increase, that would decrease your inductance. So it's obviously over much shorter space, more wire in a smaller space. So it's a bigger wall, you know, bigger wall good, because, you know, more places to reflect.
Adding a ferromagnetic core like iron magnifies the magnetic fields and significantly raises the inductance. Inductance is shown with capital L with unit of Henry, named after Henry. We can calculate inductance based on the coil geometry and core property, which I don't care about. You can use online calculators.
Right, but it's all kind of important, right? So the core size matters. These distances between the surfaces matters. All of those things will dictate how the thing functions, and I'm arguing yes, because all those things dictate how much energy you have trapped. Distance means more interactions, faster, in less time, so it's a key function. The longer the stuff has to go to reflect, the less energy it has. The less the distance it has to go to reflect, the more energy it has.
So after all this description, what is an inductor good for? What an inductor does?
So again, that's not important. So again, there, you know, this, what is it good for? You know, what kind of devices it can make, what kind of things can it do in the world? Yeah, that's all nice, but I'm just saying that's not physics. I mean, that's not really explaining how it works. So again, he's just conceding he has no clue, and he'll just keep talking about how, you know, where would we be without it?
Is that it stores energy in the form of magnetic fields in the space around it. Like I said, those fields oppose the changes in the source current, so they have energy to do it. It is like...
right, but the energy is because you trapped energy. You had to trap energy to store energy. So you took stuff that would have flown into space, and you're confining it inside of the space, and that's why you have energy to give back. It's because you have confined pressure, you have stored pressure, you've pushed things closer together than they want to be, and now you have this capacity for them to move apart because you've stored extra pressure between them.
An elastic hose. If I push water current into it, it expands and a steady flow of current goes out of the other side. But if I suddenly shut down the input current, the hose collapses and keeps pushing current out of the other side. So
as long as you don't let it come back out that side, of course. But yes, So it's the same idea. You had to trap it. And trapping it means creating more pressure. Wherever you create more pressure in the universe, you're creating potential energy. Yeah, there's nothing else to say. I mean, you either take a pressure and increase or decrease it in relative to its field, right? Because the two are going to have to be equal. If they're left to their own devices, they're going to equalize. So you have to somehow make it uneven pressure, and then you quit pushing it together and it will expand. And that expansion is another change in the pressure. The external world's going to feel the rebound. And the rebound is all you're really measuring in all of these things, is how does something rebound from what I did to it.
It opposes the sudden change of current at the input. And that's why they say a capacitor blocks DC, but an inductor blocks AC. Which is inaccurate as hell. What's accurate is capacitor blocks DC, but inductor shorts DC. So this is important. In my previous
right. So yes, there wasn't much talk about AC and DC and turning things on and off, but obviously resistance is resistance, and voltages can't be. Well, I won't explain why you can't short a high voltage with a low resistance.
ElectroBOOM 101 episode, I told you that capacitors store energy in form of electric fields and oppose the change of voltage. Now,
So again, it's not opposing the change. That's just what they're saying. It's just doing what comes natural. That is, electrons are pushed by other electrons, and electrons are attracted to protons. And that's always what's at the root of the thing, is that electrons will push on electrons. And if I make more place for electrons to flow into, if I put a field around them where there's less electrons, they'll expand into that field. They'll expand into any field that has fewer electrons in it. Electrons always want to get away from electrons.
Inductors store energy as magnetic fields and oppose the change of current. Don't forget that. And here's what we end up calculating through complex math for a relation between voltage and current of an inductor. Basically, the voltage across an inductor is equal to its inductance times the rate of current change in time. If you remember from the capacitor episode.
Alright, so there's no real point because they're measuring the current based on the rebound. It's the stored energy. So that current is just the stored energy, and they're measuring the voltage is what went in the first place. So, no point. But anyway, so I don't think there's anything else. Yeah.
The voltage across a capacitor cannot change instantaneously in no time, because that would mean infinite current through the capacitor.
Right, so that's not why it can't happen, it's because it would mean infinite current. It means that nothing can instantaneously move, and that's what these electrons are doing. They're moving. The atoms are changing shape, and they can't do it instantaneously. And you can't dissipate the pressure instantaneously. The pressure has to go through the atoms, and there's only a certain number of atoms to go through, so it's completely dependent on how many atoms you have to affect. So the thicker your wire, the more current. The thinner the wire, the less current. All that kind of, it's just kind of obvious that you can't push the force through an insufficient number of vehicles for the pushing.
Now, the current through an inductor cannot change instantaneously, because that would mean infinite voltage across it.
Look, it's like you have trucks stuck inside the coil, and the trucks can only travel road, and there's only so much road being provided by the conductor, so there's only so fast you can put the trucks onto the road, so it takes time to get the trucks on the road.
And we can't have this in real life. And that explains what happened at the beginning when I turned on LEDs by a 1.5 volt battery. When I shorted across the LEDs, I put a DC voltage across the inductor, so that...
Right, so now the inductor has a bunch of energy trapped inside of it. Okay, the coil has energy trapped inside of it. And that energy isn't relative to the voltage you put in. It's just relative to how much energy is in there in energy form. And so now the voltage can be much higher when it comes back out, because you've stored it as electron pressure, and now how high the voltage can go is going to be decided by how much energy you have actually trapped. and it's not dependent on the source anymore. So now you can greatly increase the voltage that you'll get back out of the stored energy, because you stored it as pressure. You didn't store it as this much pressure. I don't know how to say that. There's so many ping pong balls, and they're so much close to each other, and that's what you're getting rid of. That's what's going to go back out, and you can get rid of it by expanding the pressure quick, the distance quick, or releasing the ping pong balls in some other way. Well, you can't really do that with an inductor. Well, anyway, it's being stored in something more elemental than a specific voltage. So the point is the voltage that goes into the inductor is creating the pressure, but it's not, the pressure isn't dependent on the voltage you're putting in. So it's like adding charge. Yeah, that's probably a good way to say it. So you can like take something that's 1,000 volts and you can keep touching something else with that 1,000 volts, and you can keep increasing its voltage by 1,000 volts. So it goes from 1,000 volts, and you touch it again, it goes to 2,000, 3,000. You can keep adding voltage. So the inductor isn't dependent on the voltage that went in.
Current through it started to rise, only limited by the resistance of the inductor and the battery. When I opened the short though, the current through the inductor couldn't change instantaneously as the magnetic fields were collapsing. So it pushed current into the LEDs, and the voltage across them instantaneously jumped.
Alright, so there's no instantaneous. So, physics doesn't allow there to be any instantaneous, so that's just crap. So I don't know why he said that. All it is that when you turn the voltage off, now the inductor has no reason. The atoms in the wire are not misshapen anymore because of the voltage. And now they're getting just misshapen by the pressure. So they're just going to keep going from on to off to on to off. And they're going to create a current in the wire, a voltage.
To 9 volts. Also, for example, if the voltage across the inductor changes as a sine wave, then when the voltage is at the peaks, it means that the rate of current change is maximum, a positive rate here and a negative rate here. And when the voltage is at 0, it means that the rate of current change is 0, here and here. So the inductor current wave looks like this, always lagging behind the voltage by 90 degrees.
So really none of that actually happens. You're just talking about what part is the stored portion versus the original portion. So the stored portion is always behind the original portion. There's no lagging current behind voltage. Voltage is current. Voltage is pressure. Pressure moves based on how many atoms are available to be pressurized. The more atoms available for being pressurized or pushed, then the higher the potential current.
Like a capacitor current that always leads the voltage by 90 degrees. And there we have it.
Yeah, so that's just mushy. That's just a mathematical representation of the fact that it takes time for the energy to get out of into and out of the inductor. It takes time for the pressure inside here to hit the wires, go through the wire, and get somewhere.
Enough details for one episode. Inductors are beautiful components, like Skillshare, the sponsor of this video.
Alright, so he never got to magnetism at all, so, false title. Didn't explain how it works at all. Nothing. So anyway, enough of a video, I think. Tired. It's depressing. So anyway, this is what the world rewards. Not saying much about the world, frankly. Yeah, standards are pretty low. Until the next time, and such. Ugh.